Um, okay, folks, we're happy to have Zeyu Wang from Hong Kong University of Science and Technology. He's an assistant professor of computational media and arts there. And he actually just joined the department. He defended his PhD work at Yale University a couple of months ago, just the middle of summer. He did his PhD on, well, you'll hear about that work, interactive systems with the supervision, under the supervision of professors Julie Dorsey and Holly Rashmeyer. I met Zeyu back when I was on a sabbatical at Yale University back in 2016, 2017. Even then he was working on the early versions of his thesis work. His current research interests lie at the intersection of HCI, computer graphics, AI, with sprinkles of machine learning. And he's specifically interested in sketching and mixtures of virtual reality, augmented reality, generative techniques. Since he just defended, the work that he will talk about is very fresh, fresh off the oven. So we're very pleased to have you, Zeyu. I'll leave the floor to you now.
Thank you so much, Madin, and it's my pleasure to be here today and share my work enhancing the creative process in digital prototyping. So during the talk, if you have any questions, feel free to leave that in the chat pod or raise your hand and let me know, and we can discuss at any time. So I'll start by talking about we as humans have a creative instinct. You know, from traditional Chinese paintings to sculptures in the Renaissance, our works across the world demonstrate the cultural, social, and scientific value of content creation. And the history of content creation is also a history of co-evolution of art forms and the tools people use to create them. For example, ink brush, mineral pen, hammer, and chisel all play a critical role in creating these artworks. Over the past few decades, digital technology has revolutionized content creation. Dating back to 1963, Ivan Sutherland, back at MIT, invented Sketchpad, the first program ever to utilize a complete graphical user interface, laying the foundation for modern computer graphics and computer-aided design. Another significant milestone was back in 1995 when Pixar released Toy Story, the first full-length 3D computer animated film. Toy Story was made using a new graphics system called RenderMan, developed by a team led by Pat Harahan and Ed Catmull, and many features in this system have become industry standards. Today, digital content has become ubiquitous. New techniques for 3D modeling and rendering have brought computer-generated imagery to yet another level. Many applications from feature films to video games rely heavily on digital content. And digital content creation is estimated to have a global market size of hundreds of billions of US dollars. However, many tools in the digital workflow have a steep learning curve. If you've ever used some of the heavyweight software, you probably have come across some unintuitive interactions. For example, when the famous architect Eero Saarinen designed the Ingalls rink at Yale, he used the sketches on the left to convey visual forms and explore design ideas. But on the right, if someone were to model Ingalls rink in Maya, countless buttons and panels would be so intimidating if they hadn't been trained to use this specific software. Now we can have a big picture of one of the biggest challenges in digital content creation, that is unintuitive prototyping. Sketching on paper, despite being 2D, is spontaneous and flexible. It can quickly convey the visual form in just a few minutes. And it is suitable for prototyping and exploring ideas. In contrast, many current tools for digital content creation still rely heavily on buttons, drop-down menus, and sub-windows, often leading to unintuitive interactions. Manipulating 3D content on a 2D desktop can also be difficult, and it usually takes a lot of time and effort for users to iterate design ideas and create intended content. In another example, the character in this animated short film wanted to make herself prettier. But when manipulating the geometry, due to complicated interactions, she mistakenly used tools like merging, extrusion, and subdivision, leading to a total disaster. And from this, we can see the steep learning curve and unintuitive interactions in current graphics software. So a key question I'd like to raise and address in this talk is how can we build digital tools that support rapid prototyping and provide an intuitive content creation experience? I think in order to provide a more accessible and intuitive prototyping experience for content creation, digital tools should understand and leverage users' creative process and spatial context. This calls for joint research effort in computer graphics, as well as human-computer interaction and AI. I will present a series of studies, techniques, and systems for enhancing the creative experience along 3 thrusts: drawing, augmented reality, and time-based media. Here is an outline of my talk. First, I will present a drawing dataset and spatial temporal analysis that provide insight into people's drawing process and its difference from computer drawings. I'll then talk about an interactive system for line drawing animation that achieves efficient deep learning-based synthesis conditioned on user-created keyframe drawings. In augmented reality, I will demonstrate the importance of utilizing spatial context through 2 tablet-based interfaces. The first one is the Sensi AR, which enables designers to create site-specific AR experiences for remote environments. I'll then introduce Point Shop AR, which integrates point cloud capture and editing in a single AR workflow to help users quickly prototype design ideas in their spatial context. Last, I'll show 2 procedural methods to generate time-based media that are easy to consume by other people, which facilitate the dissemination of creative and cultural ideas through visual communication and storytelling. To build tools that assist content creators, we first need to understand how humans create, and especially how it differs from computer-generated content. Here we begin with a comparison between how humans and computers draw, as drawing is a fundamental medium for exploring and communicating visual ideas. We know the computer graphics community has long been interested in developing methods to approximate what people draw. Computer-generated drawing approximation, or CGDA in short, can be divided into non-photorealistic rendering, NPR, that takes a 3D mesh model as input, and also image processing that takes the 2D raster image as input. These computer-generated drawing approximations are often used as a proxy for hand drawings. However, it still remains unclear how much these computer drawings resemble real drawings. In particular, most CGDA methods only approximate the end result, neglecting the drawing process, which includes stroke and temporal information. This shows the importance of collecting and analyzing actual drawings so we can better model the drawing process and inform new algorithms. Here, we consider 2 common forms of drawing, tracing and freehand. Tracings are easier to obtain than freehand drawings and are registered to images by definition. Like freehand drawing, tracing can also provide temporal information and stroke demarcation. The art community has long discussed the distinction between tracing and freehand drawing. For example, tracing is believed to help artists understand structure and perspective, but it also can discourage detailed analysis of the work and become a crutch. However, there is a lack of quantitative analysis, partly due to the lack of datasets that are readily applicable to the comparison between tracing and freehand drawing. In our study, we included a total of 100 photorealistic images as prompts. These images cover a wide variety of shapes and appearances. We collected 1,210 tracings from 96 participants and 288 freehand drawings from 19 participants. Here you can see a sample of our collected drawings, with temporal information and diverse artistic styles. After the drawings are collected, we first need to register freehand drawings to tracings in order to do a comparison. Our approach was a coarse-to-fine optimization of image correlation between freehand drawing and tracing density, and you can see the optimization process on the right. We start our analysis by exploring whether people trace and draw similar content using rasterized drawings. For each pixel in the drawing, we compute a pairwise distance as the closest distance to any pixel in any other drawing. So in both tracing and freehand, over half of the pairwise distances are within 4 pixels. And this corresponds to the commonly drawn content, such as contours as shown on the right. About 15% are 20 pixels or more, which represent strokes distinct from each other, such as the diverse choices for shading as shown on the right here. We found that in both tracing and freehand, people tended to draw more common pixels early. People preferred finishing the entire outline first in tracing, as opposed to decomposing the prompt into parts in freehand drawing. The raster representation showed what people draw in common, but it missed stroke information. We now look into whether people use similar strokes using recorded vector data. We extracted a list of stroke features and examined how they change over time. For example, you can see in the first row, stroke length tends to decrease over time. Drawing speed tends to increase over time, and stroke opacity tends to decrease over time. So we found that in both tracing and freehand drawing, early strokes tended to be long and drawn slowly using opaque colors, whereas late strokes tended to be short and drawn quickly using translucent colors. So what does that mean? Next, we examine whether tracing and freehand drawing evolve similarly based on that observation. We labeled strokes based on drawing intention and observed that drawings progress similarly in tracing and freehand. So we can see that the silhouettes were dominant at the beginning, shown in orange, and hatching strokes became more prominent towards the end, as shown in blue. Such trends suggest the possibility of stroke classification using stroke features. So here we show sample labeled tracings used for training random forest classifiers. The classifier trained on tracings not only performed well on other tracings, but could also be transferred to freehand drawings. Here you can see that orange represents contour strokes and blue represents tone details, and the classifier performed well on both tracing and freehand drawing. After comparing tracing and freehand, we now evaluate how much current CGDA output and hand drawing overlap. We found about 60% of drawn content is consistent with computer-generated output. As you can see here, NPR methods captured contours but did not consider texture information. Some image processing results contain incomplete or extraneous edges. Compared with CGDA results, drawings were cleaner, more organized, and contained interesting strokes that depict tone and shading. Finally, we examine how computer-generated drawing approximations correspond to common strokes. For each stroke, we computed a common score and CGDA score. We can see that early strokes tend to have higher common and CGDA scores. So the blue strokes on the left correspond to warm yellow and also red strokes on the right. So we did a correlation analysis, and it suggests that CGDA can capture content that people commonly trace and draw, but not their diverse artistic conventions. To sum up, our dataset and analysis review the similarities and differences between freehand drawing, tracing, and computer-generated drawing approximation. We found that tracing is similar to freehand drawing in terms of temporal tendencies and representation choices, and thus can serve as a viable proxy for drawing. An analysis of the drawing process suggests that people's intention evolves over time, which can be characterized by similar spatiotemporal stroke features. Current CGDA and image processing results only capture about 60% of drawn pixels on average, highlighting the great value of collecting hand-drawn data. If you're interested in looking at our dataset, feel free to check that out in this link below. So we think our dataset analysis can be useful for many future applications. For example, our dataset enables learning the mapping between an image and people's drawing density. In an ongoing project, we are developing data-driven NPR methods that better emulate the drawing process based on our analysis results of how humans draw. So we can see that the artist drew contours first, followed by hatching strokes, whereas current machine predictions fail to capture such trend. Finally, it would be very interesting to use stroke type recognition for better shape inference. Here in this visualization, we lifted different types of strokes into 3D and explored how they can be viewed from different angles. Next, I'll introduce an interactive system for user-controlled synthesis of line drawing animations inspired by the previous analysis. In our analysis of how humans and computers draw, we found that current computer-generated drawing approximations are not capable of representing the diverse drawing styles that people employ. Even though there are multiple NPR methods, there's no straightforward way to adjust thresholds or interpolate different methods in order to match a user-created drawing. And this is one of the reasons why many artists still prefer drawing on their own over computer-generated results. Particularly in the case of animation, animators often need to draw many sketches frame by frame, even though it is a tedious process. Wouldn't it be great if we develop a method that can make line drawing animation easier while allowing user control, so we can get the best of both worlds? Here we envision a system that takes animated 3D models as input, and the user only needs to provide a keyframe drawing at the bottom left corner. Then, drawings at all other frames will be automatically generated in a style consistent with users' expectation. And the user should also be able to add a new keyframe drawing, and the output at all other frames will be automatically updated by propagating and interpolating the user's drawing style. Technically, we formulate this problem as learning a style space for user control. Here, we show a style space expanded by commonly used NPR output, including contours, suggested contours, ridges and valleys, and apparent ridges. Given a user's drawing and its corresponding geometry, we want to learn a latent style descriptor, so the user's drawing style can be transferred to other frames. Our goal is to create an interactive system for synthesizing line drawing animations. Given a sequence of 3D models, an animator creates drawings as some keyframes, and we expect the system to learn the styles and propagate or interpolate to all other frames. The animator then can refine certain frames and iteratively edit the animation. Our approach is based on generative adversarial networks, or GANs, that have proved effective in image synthesis tasks. Here we use a GeoNet, which encodes the map of geometric properties MA at frame A. We also use a StyleNet, which encodes the style of a drawing IA to a latent vector Z. Then, the generator can use the geometry code and the style code to generate a drawing in the same style. To train this network, we first generated a 6-channel map containing geometry space and image space features for each frame. We included the production of normal and view vectors, the depth map, and 4 types of surface curvatures used to generate commonly used NPR renderings. We then generate a synthetic NPR dataset for training. For each frame of an animated character, we combine contours, suggestive contours, ridges and valleys, apparent ridges, and canny edges using different thresholds and generated 68 NPR line drawings of distinct styles. One important property of this network is that the style net should be disentangled from the geonet. In other words, in the lower branch, no matter if the input is frame A or frame B, as long as the drawings are the same style, the encoded latent vector Z should always be the same. Therefore, we use an intrinsic loss during training to enforce this property. We also came up with a few new loss terms for smooth interpolation in this specific task. As shown at the bottom, case 1 is an ideal case where the stroke grows smoothly. Case 2 and case 3 are counterexamples. In case 2, a stroke overgrows and then shrinks. In case 3, a stroke grows in fragments. Our design of the interpolation loss and also the strokeness loss will make the network prefer the ideal case 1. Since the network is trained on synthetic line drawings, we cannot expect it to perform very well on user-created drawings because it hasn't seen those styles before. To make it generalized from NPR to actual drawings, we use an optimization-based method to get the input drawing embedding. As shown at the bottom left, the initial reconstruction from Z0 is quite different from user input. We optimize the latent vector Z with all the weights frozen in the trained network, so the drawing reconstruction from the optimized latent vector Z star can be very close to the target. Now, I'm going to show some results of style transfer to another frame. Here, if we input a drawing with a particular style at any frame, the output will be very close to the target. Here, the girl on the left uses a suggestive contour style, and the mouse on the right uses a canny edges style. We then show how it can interpolate between two user-edited drawings on a static frame. We can see our interpolation results in the top row, whereas stroke appear and elongate smoothly. In contrast, the baseline interpolation using vanilla GAN failed to generate a meaningful interpolation. Here we can see the animated results for the girl character. Similarly, our method interpolates smoothly on the mouse character, whereas the baseline interpolation using a vanilla GAN failed again. Here we can see the animated results for the mouse character. Finally, we show how our method can support an interactive editing workflow for a dynamic sequence. Here, the user only creates one keyframe drawing in the red box, and their style of simple contours is automatically propagated to all other frames. Here we can see the animated result. If the user creates another keyframe drawing with a different style, say with all the folds on the skirt, our method can interpolate between these two styles in the in-between frames. Here is the updated animation. The user can create a new drawing if not satisfied, and the drawings will be automatically updated. And here's the new animation after this change. Finally, the user can also remove a keyframe drawing to relax the constraint, and we can see the frames at the beginning are also updated. And here is the final animation after all these iterations. To sum up this part of my work, we propose a deep learning-based method for interactive line drawing synthesis from animated 3D models. The learned style space is disentangled from the underlying geometry, enabling smooth style interpolation on static and dynamic frames. This is an effort in user-centric algorithm design, which helps us move closer to the best of both worlds, that is user-controlled synthesis. Some future work includes getting more training data through sampling more NPR parameters and also using more NPR methods. So we can expand a style space more descriptive of actual drawings. Learning with a vector representation and factoring in dynamics in drawing are also very interesting directions. So far, I have introduced how to understand and leverage the creative process in drawing. In the next part of my talk, I'm going to address how we can make use of spatial context to facilitate design prototyping in augmented reality. In fact, drawing and AR are two types of media very suitable for prototyping. Drawing reflects designers' perception and mental representation of the physical world, and therefore has been a time-valued tool for design prototyping. One of the reasons why people chose to stick with drawing in 2D is that traditionally, it was too difficult to obtain 3D spatial context, and there was a lack of intuitive tools to directly manipulate them. With the advances of hardware and software, today's augmented reality can serve as an interface between designers and the physical world. Modern sensors can effortlessly perceive the environment and provide instant spatial context for designers. We now explore how to develop AR tools that can enhance accessibility and versatility in 3D design. I'll first present Distancy AR, a workflow for authoring site-specific AR experiences for remote environments. We know most AR authoring tools only allow designers to create experiences for their current environment, like adding a virtual table and chairs to an empty room. However, more and more designers need to create AR experiences for a remote environment due to COVID and travel restrictions. This is challenging due to the disconnect between designers' physical context and the remote environment. For example, if designers create an AR experience for a remote living room from their office, it is often hard to navigate and locate objects. In Distancy AR, we first capture a remote environment using a LiDAR-equipped iPad. Using RGBD images and camera tracking information provided by Apple's ARKit, we can quickly acquire a 3D scan of the remote environment. To add color information to the 3D geometry, we generate the texture for the 3D scan by projecting pixels and using pyramid blending. Normally, after we have a 3D scan, a typical approach to remote AR authoring would be to import the scan to 3D software like Blender and add additional objects to the scene. But as you can see, current solutions do not provide an AR-like experience, and users often have trouble creating because of unintuitive interactions for navigation and manipulation. With the scan of the remote environment, our Distancy AR workflow provides a tablet-based authoring interface for designers to create AR experiences at another location. Once the creation is complete, viewers can go back to the remote site and consume the created AR experience in situ. Our baseline interface simulates the experience of using in-situ AR authoring tools. In this portal mode, designers can see a 3D visualization of the captured environment, even if they are physically at another location. They can walk around and place virtual objects, such as a couch, and move it next to the wall. And they can also put a table in the middle as if they are on site. We conducted a formative study by asking 5 participants to furnish an empty kitchen in a dormitory. We collected their feedback to identify challenges when they were using the baseline authoring interface. We found that in a successful system for remote AR authoring, authors should be able to freely navigate a large remote environment in a small physical space, understand the layout and appearance of the remote environment, and also experience their creation as if they were using AR on site. We need to improve the baseline system to address these issues. So what we did was to incorporate a new dollhouse mode to enable free navigation in a small physical space. We also incorporate a new peak mode to help designers better understand the remote environment. And we keep the baseline portal mode to allow designers to experience their creation as if on-site. In the dollhouse mode, designers can transition to a bird's-eye view from the first-person view. They can keep adding objects in the dollhouse mode with a better understanding of the entire space. They can also move the avatar to a corner in the room and transition to that location to examine the added virtual objects. The peek mode brings designers' viewpoint in the 3D capture to the closest one with a captured image, so that they can examine how their design looks like in the real environment and compensate for badly scanned parts like specular surfaces. They can move the tablet and retrieve a series of captured images that simulate their movement. The technical problem here is to choose a frame from the captured video given the current AR camera, so that the retrieved frame most closely matches the AR view. While there are many techniques dedicated to view interpolation, they needed a lot of computational power, which was not possible on a tablet. Our quick approach minimized the cost between the recorded view and the current AR view. And we found mesh coverage to be the most robust metric to use to define the cost function. So mesh coverage is determined by the camera pose and mesh geometry. We measure mesh coverage using downsampled binary UV maps. So with the current AR view, frame J is retrieved because its UV coverage map is most similar to the current AR frame's UV coverage map. We evaluated the Distancy AR workflow with a remote user study. We recruited another 10 participants and asked them to furnish the empty kitchen. They used both the basic system containing only the portal mode and the full system containing all 3 modes. Based on ratings of the 2 systems, we found that dollhouse and peek modes made it significantly easier for participants to understand and navigate the remote environment. For each participant, we visualized mode usage over time for the improved system. They still spend substantial time in portal mode, highlighting the importance of being able to experience the creation as if on-site. We found that participants frequently switched between portal and dollhouse modes to understand the space and refine the design. They also tended to use peek mode towards the end to validate the AR experience with captured images. In summary, our remote AR offering workflow allows designers to keep creating using familiar and intuitive AR interactions, no matter where they are physically. This will also encourage remote collaboration, as working remotely has become a new normal. Our spatial representation enhances accessibility and editability in AR prototyping, and the time-based analysis in the user study reveals common tendencies of AR designers. Our Distancy AR system allows users to import virtual objects to a LiDAR capture, but oftentimes designers need to modify their current spatial context directly to explore design ideas. Next, I'm going to talk about another tablet-based system called Point Shop AR, which provides a single integrated capture and editing workflow using the point cloud representation. Let's say I'm a home designer and my client asks me to renovate their house. I need to explore many environmental design ideas and visualize changes to the physical environment, such as how their home will look like if I open a window on the wall and remove a closet. This can be very costly if I iterate my design physically. Modifying a replica of the environment would have been easier, but traditionally, I would need to measure the physical dimensions. I then need to build and edit 2D blueprints and 3D models in some CAD software. And this has a steep learning curve and requires years of training to master. We conducted a formative study by inviting 6 professional architects and asking them to reflect on their recent projects. The goal of this formative study was to understand how they use spatial context in their design practice. We found that designers would like to capture their spatial context easily and quickly, edit the capture in a representation amenable to rapid prototyping, and also be able to experience and iterate their design in situ. Based on these findings, we designed PointShop AR, a novel tablet-based AR prototyping pipeline that uses point clouds instead of 3D models and integrates capture and editing in a single application. The user can use an iPad to capture and edit point clouds, and the server will take care of other necessary computation. In PointShop AR, I can use the LiDAR scanner available on consumer tablets like iPads and quickly capture my 3D spatial context. I can load the capture in the form of a color point cloud in just a few seconds. And then I can walk around to view my scan in AR. I can use the same device in the editor mode to perform a variety of point cloud editing operations, such as opening a window on the wall by importing an earlier scan from another room, and I can then remix it with the current environment using touch-based object manipulation. I can select the closet by tapping a bunch of points on the object to create an initial bounding box. I can then rotate the bounding box and adjust the faces of the bounding box to make sure it covers the object I want to select. Once I'm done with adjusting the bounding box, I can tap the Separate Points button to cut out the closet out of the original scan. I can then remove it. To fill in the hole, I can use the inpainting feature and tap a few points on each of the 3 planes and send a request to the inpainting module on the server. A point cloud patch can be generated in just a few seconds to fill in the hole. I can then import a desk and put it next to the wall. And I can also import a chair and put it next to the desk. I can also use the grabbing feature to open the door. So while I'm holding the grab button, the iPad's motion is mapped to the virtual door. And finally, I can add a keyframe and use the animation feature to show the door opening process and make sure it doesn't run into the desk. And here is my final design for this new living room. PointShop AR has many application scenarios, such as turning a square desk into a drop-leaf table. We can also convert a trash can to a stove by removing the lid and adding points for the flame. We can convert a bedroom to a dining room by removing the bed, fitting the hole, and importing a table and chairs scanned elsewhere. We can also make the window wider on this house and add another door. And we can also redesign a backyard by removing the plants and adding a new picnic table and a tree. In the last example, we show a redesign of a living room where parts of the wall behind the TV set was removed. Comparing the recording of the physical environment and the recording of the edited point cloud, we can have an intuitive in-situ experience of the new design. Residents will have a more direct access from their bedroom to the living room, as you can see here. We invited 7 participants to a remote user study to evaluate the PointShop AR system. We can see that they spend about a minute to scan their environment and up to 21 minutes to edit the scan. They performed a variety of editing operations, such as replacing furniture and adding fan animations. Overall, most participants felt that it was easy to capture the environment for their design. It was also easy for them to understand the space by looking at the point cloud, and it would have taken much longer if they did this design physically. Among all the features, participants liked point cloud capture and import-export most, as they are the foundation for remixing point clouds. Their ratings of selection, manipulation, and animation were also mostly positive. To sum up, in this project, we present an initial set of point cloud operations that are analogous to those in Photoshop. We chose to use point cloud as the underlying representation, achieving a balance between reconstruction quality and prototyping speed. PointShop AR enables an integrated capture and editing workflow on a single mobile device and demonstrate that point cloud is suitable representation for rapid AR prototyping. Some future work includes sketching with point clouds to provide a more fluid experience, and new techniques for point cloud rendering and editing, such as shape abstraction, instance segmentation, texture-aware inpainting, and tools for spraying, morphing, and sculpting points. In the last part of my talk, I will briefly describe two procedural methods used in AnyCode and Cherub for generating time-based media. So far, we have discussed methods and systems that enhance the creative process for content creators using drawing and augmented reality. The final step of content creation is often to create media that are easy to consume by other people. Time-based media, such as videos and synthetic animations, are replacing text and static images and have proved effective in visual communication. In our AnyCode project, we investigate how to communicate a video without internet access for accessibility and privacy purposes. We approach this by dividing the communication process into two parts, authoring and consuming. Both the author and the consumer rely on a single image to design and decode an animation. The key technique here is to convert an animation to information that can be put into a QR code, including landmark coordinates, image segments, and animation parameters. AnyCode has many applications. For example, at the airport, an international traveler may wonder how to find the connecting flight. The traveler may not have internet access in the new country. In this case, decoded animation can show them how to navigate through the airport without network reliance. And here is how we use the ink stick to grind ink. AnyCode can also be used in interactive art posters, like this famous illusion. It can also demonstrate configurations of building blocks and make chess notation more intuitive in this interactive animation. Finally, AnyCode is also useful for outdoor scenes. For example, when your car broke down in the mountains and you have no internet access, it can show you what you need to fix under the hood. Next, I'm going to talk about Cherub, an open source software package for visualizing heterogeneous data in cultural heritage research, including 2D photos, 3D models, and reflectance transformations. Researchers can collaboratively annotate and make sense of raw data and share their findings with the public. For example, this cuneiform tablet records the Pythagorean theorem. Driven by expert annotations, we developed an automatic video generator that gives a virtual tour within a cultural heritage site. The viewers can easily associate visual information with text provided by the experts to understand different meanings of the artifacts, such as a nobleman smoking tobacco, an Arabic calligraphy decoration, and also a puppet show theater. Another or recent project explored how to reconstruct an ancient site in Syria called Dura Europus. Because we only have a sparse photo collection, they were taken at different times and have varying quality, photogrammetry was not a good solution. What we did was to extract key contours from them and projected the strokes into 3D to quickly generate a video fly-through like this, so viewers can easily get a sense of the space. In conclusion, My talk presents a collection of studies and tools for enhancing the creative process in digital prototyping through 3 thrusts of work in drawing, AR, and time-based media. I've shown that understanding and leveraging the creative process and spatial context of content creation and consumption are key to an intuitive and user-centric experience. In drawing, our analysis of the drawing process reveals the limitations of current computer-generated approximations and informs future intelligent drawing interfaces. I've shown that designing generative models with an eye to intuitive user control can make content creation more efficient while respecting people's creative input. In augmented reality, I've shown that LiDAR scans using available consumer tablets like iPads can improve accessibility and AR prototyping for remote environments. Representing spatial context using point clouds can support an integrated capture and editing workflow on a single device for more versatile AR design. In time-based media, I've shown that content creators need to consider the types of media that are easy to consume by other people. Our video generator design based on a set of procedural animation schemes can facilitate the dissemination of creative and cultural ideas. Finally, I'd like to talk about future directions of digital content creation and AI technologies. As we see, failure to understand users' creative intention is the key reason why many digital tools have a steep learning curve and are unintuitive to use. The fact that people still often have great difficulty learning and using digital tools shows that a productive research mindset should focus more on developing intelligent tools that assist content creators rather than building AI models aiming to replace human artists. With recent advances in AI, there have been some AI models that attempt to create art. For example, Google collected a dataset called PicDraw containing 50 million sketches from a Pictionary game. They trained a recurrent neural network to generate symbolic sketch given a text prompt. And just within this year, many text-to-image AI models like Imagen and DALL-E 2 have brought breakthrough impact on AI art creation. Another neural painter can take an image as input and generate a sequence of brush strokes that emulate the painting. These techniques can produce interesting results, and many believe these are advanced enough to represent content creators. However, these techniques do not necessarily incorporate artists' and designers' workflow, which involves progressively expressing creative intention and utilizing spatial context. For example, when an artist paints a moonlight, he first paints the background using ambient colors, then draws the landscape, moon in the sky, reflection on the lake, and finally trees by the lake. The artist used diverse paint colors and brushes that reflect his thought process and approach to art. In comparison, the AI-generated painting sequence did not capture this complex process. Instead of semantically meaningful strokes, we see strokes fill the canvas randomly in a robotic manner. In my opinion, all this effort needs interdisciplinary research. This is not only about applying existing computer algorithms to other fields. Theoretical and practical challenges in other fields also inform and motivate future research directions in computer science. So what I'm focusing now is creative intelligence and pursue more interactions between scientists and artists. So here I'll use an example to demonstrate how people from different backgrounds would think differently. On the left is a famous sketch by Pablo Picasso. And if you ask the person who had no art training to draw this, they will probably draw something like what's on the right. Artist Betty Edwards pointed out in her book, Drawing on the Right Side of the Brain, that if we observe and draw upside down, it will temporarily suppress semantic understanding and encourage us to focus on the relative geometric relationships. So I did this myself. When I put my drawing right side up, to my surprise, I found my drawing exceeded my expectation by really a lot. So this shows that learning to draw is actually learning to see. Sometimes semantic understanding would be an obstacle for novices to excel at drawing. Currently, there is much AI research on semantic understanding, but far less that aims to model and assist people's creative process. Here's another example where AI researchers proposed an automatic method for interpolation, but faced a backlash from animators. One animator said on Twitter that every single frame has its own intent. Animators make sure of perfect timing, smooth action, and so on. And interpolation literally destroys the line work. So when we look at these examples, we can feel for the animator community. Even though FPS was raised from 24 to 60, much detail of the sparkle was missing in the top row. And in the bottom row, there is even a very weird shape at the character's hand. So this shows that digital technology needs to understand rather than dictate creative intention. My vision for the future is what I call synergistic creative intelligence. Seeing how technology has revolutionized our current life, many people would deem AI as a potential threat for artists. However, I would say that this depends on how we define and position AI research. Instead of replacing the artist, AI should offer better help to the artists. It's just like people are never afraid of cars, even though cars are much faster than humans. In 1839, French artist Delaroche has made a famous statement, "From today, painting is dead," after he saw the works of modern photography. However, we've seen that the advancement of technology does not end the era of painting. Rather, it inspired artists such as Picasso and Mondrian, who represent Cubism and abstract expressionism. Despite effort presented in this talk, there are actually many challenges in digital content creation that still remain. This is evident from countless dollars and hours spent by creatives around the world. I think computing should further support creativity by informing creative intention, reducing tedious repetition, and exploring broader design spaces. Since digital content creation has been ubiquitous these days, intuitive digital tools for creating them are just like the new coal and electricity in the next technological revolution, be it metaverse or whatever we want to call it. I hope we can soon be closer to the goal of creativity for all through joint research efforts from different disciplines. There are many exciting future directions in the field of digital content creation. For example, the first one is intelligent drawing interfaces, including how to help novices better learn drawing and infer 3D information from the artistic attributes of the strokes. The second is multimodal AR interactions, such as how to free users from the unintuitive interactions with traditional 2D desktop software when creating 3D content. The third is datasets for creative intelligence. Compared with datasets in AI for image recognition, datasets of people's creative processes are still very lacking, which limits the development of intelligent tools for content creation. And next is user-centric generative techniques, such as more intuitive control of generative models, avoiding tuning dense parameters and graph nodes while leveraging its expressive power. I hope advances in these areas can boost everyone's creativity and democratize content creation. And this is the end of my talk. I'd also like to mention that my research group at KUIS has several PhD and postdoc openings, and we offer an interdisciplinary environment, new research facility, and globally a competitive stipend. So feel free to send me an email if you're interested. And I'd like to thank you again for being here today, and I look forward to any questions you may have. Thank you.
All right. Thank you, Zeyu. This was such a great talk with many lines of work, all with substantial and very interesting contributions. I'm actually very impressed. I'm specifically also very impressed about how you put the field-specific view of these different kinds of media into perspective, because a lot of the times in computer graphics and in computer vision, people tend to treat all images the same as collections of pixels, but a painting is different from a photograph, which is different from, say, a cartoon. All these different kinds of media mean different things in their respective fields. So putting that into perspective, I think was very useful. I hope other people also pick up on this view of the richness of the media. We have 5 more minutes, so I'd like to open it for questions. I'm sure people have questions. So questions, folks? See. Okay, I'm gonna ask a question myself. In the meantime, if you do have a question, please raise a hand. Okay. So Zeyu, in your work, especially in the earlier pieces of work that you presented here, you talked about representation, the choice of representation, whether it be vector representation or point cloud representation, raster representation, and going to vector representation was actually in one of your future works when you presented. So what's your view on the advantages and disadvantages of these different kinds of representations? Again, the vision community is mostly interested in pixel-based representations. Computer graphics community is mostly interested in, say, volumetric or shape-based representation, triangulated representations, etc., graph-based representations. What's your view on the strengths and weaknesses of these different kinds of representations? I think you've mostly worked on the raster side again, right?
So yeah, that's a great question. So I think, visual computing in general, like including graphics, vision, visualization, I think, we deal with different representations every day, from pixels, vectors, to points, volumetric data, things like that. So I do think there are different advantages. I think especially for pixel or raster representation, the vision or AI community have studied this very well. If you look at GANs and stuff, you can generate very realistic images. But actually, there are a lot of things that are missing in raster representation. So for example, in my first work, like the top left corner, in our analysis, we actually compared both raster data and vector data. So it did this stroke level analysis to see whether if you draw a stroke, if this stroke is contour or hatching, because they have different meaning or different creative intent. So I think a future direction is, how can we combine the power of deep learning with the expressiveness of vector, or the precision of vector information. So if you look at the example here, this guy did this kind of animation interpolation, frame interpolation, FPS from 24 to 60 grade, but because they used a raster representation, all the sparkles, all the details, all the creative intents are kind of lost in this result. So this is one of the reasons why their AI interpolation was opposed by professional animators. So I think if you have a better representation, be it vector or maybe a hybrid representation, I think there's a lot of work we can do to make this AI-assisted content generation much better.
Mm-hmm. And I also have a follow-up question. So in the earlier work, again, you talked about these contour, strokes, ridges, edges, shading, strokes, etc. Did you actually have these manually annotated for the drawings that you collected? Also, like the computer-generated one, did you have you or someone else manually annotate these strokes or pixels, saying these look like edge pixels or ridge pixels? Yeah, I saw this. I was just not sure if this was based on some temporal labeling that you did, or did you go ahead and individually label each pixel, each stroke?
Yeah, so that's a great question. So in this particular case, I myself labeled a bunch of drawings here. So like, we collected quite a few tracings drawings, and I just go in the drawings and label each individual stroke, be contours or shading, something like that. So a part of drawings in our data set are labeled like this. All the strokes are labeled. So all the information is in the GitHub, and feel free to let me know if anyone need to use that information. so we can pursue this even better.
Cool. And did you connect this to a classification pipeline as well? I might have missed that part.
Yeah, something like that. So we have stroke features like, speed, time, length, all sorts of features. And we also have the labels. And we see how the stroke features changed over time, and also how drawing intention changed over time. So naturally, we can build this classifier, and it performed quite well. Especially, you can imagine classifiers trained on tracings can also perform well on freehand drawings. So we can see like a kind of a transfer learning there.
Okay. Again, thank you for this great talk, Zeyu. And for everyone else who might still have questions, I will arrange another meeting, more informal one-on-one meeting with Zeyu in the following days. So if you would like to join that meeting, just drop me a note so we can have you in the loop as well. And I'd like to thank everyone for joining in today. And thank Zeyu again for the great talk.
Yeah, thank you. Thank you guys so much for having me.
All right. Goodbye, everyone.
Bye.